Let's check if this improper integral converges or not. This is the integral from 1 to infinity x plus 1 over square root of x to the fourth power minus x. In fact, this is both type 1 and type 2 situation. It's type 1 because we have from 1 to infinity, the infinite interval. And it's type 2 because when x is equal to 1, we will get 0 on the denominator. We have a vertical asymptote when x is equal to 1. And we cannot really deal with both type of improper integral at the same time. So we are going to break this into two pieces. So we first pick a number between 1 to infinity, let's say 2. I will break that down from 1 to 2 as the first part, and then for the second part, I will pick up where I left off with, which is 2, and then go all the way to infinity. And you see, this integral right here, it's only a type 2 situation now because we only have a vertical asymptote when x is equal to 1. And this right here, it's only a type 1 situation now because we only have from 2 to infinity. And this right here, it's a continuous function on this interval. Another reason why you have to really pay attention to these kind of things is because, let's recall the comparison theorem for type 1 improper integral. To use the comparison theorem, we must make sure that the function f and g, they have to be continuous for all the x value greater than or equal to a. And then you see, we can compare this integral from a to infinity of f of x, and then the integral from a to infinity of g of x. So we cannot really deal with this limit from 1 to infinity because when x is equal to 1, this function is not continuous. So we have to break down into two pieces, all right? Anyways, now let's pick out something that we can handle it much better because this is kind of hard to integrate. So we have to come up with a much easier improper integral, and then we can make some comparison. And to do that, when we have that x is toward infinity, let's just pick the highest power of x on the top and on the bottom. On the top, we have just x. On the bottom, we have the x to the fourth power, but that's inside of the square root. So this is square root of x to the fourth power. And then we can simplify that. X on the top over square root of x to the fourth is x squared. And then we can reduce this to 1 over x. And now what? This is just the expression. We still are talking about integrals, right? So this is the integral, and then put on dx right here. I have two parts right here. Which piece should we compare with? Let's look at the first one. It goes from 1 to infinity. It goes from 1 to 2. If you want to just put on 1 to 2, guess what? This is not even an improper integral because when you have 1 over x, there's no vertical asymptote between 1 and 2. And then from 1 and 2, it's just a finite interval, isn't it? So I'm not going to use this and compare with the first piece of the interval right here. And I'm actually going to use the second one. So I will pick from 2 to infinity. And as you can see, now I'm pretty much following the conditions of the comparison theorem. Both of the function, 1 over x, and this right here, they are continuous from 2 to infinity. Okay? And does this converge or not? Well, let's just do this real quick. Let's integrate that. The antiderivative of 1 over x is ln x, and we are going from 2 to infinity. They are both positive numbers, so, well, infinity is not a number, but they're positive. So I don't need absolute value. And then you can just plug in infinity like this. ln of infinity and then minus ln of 2. Well, ln of infinity is infinity minus the finite number is still infinity. In another word, this right here, diverge. Okay. So I hope to use this to help me compare with that and then draw a conclusion. And because this is the divergent, to make a connection, I would like to show this. It's bigger than the divergent. Because remember, this situation, this is a diverge to infinity situation. If we can show that this is bigger than infinity, this one has to be infinity as well, right? It's even bigger. So I will just put on the expression x plus 1 over square root of x to the fourth power minus x. I want to show this expression is bigger than or equal to 1 over x. Okay? And then this, I hope to show that it's true for x is greater than or equal to 2. And then notice that because we're talking about x is greater than or equal to 2, 1 over x will be positive, and then this right here will also be positive as well. So I should technically include that, because remember, the f and g function, they have to be positive to be technical. And then I don't know if this is true or not, so we will have to work out the algebra now. If this is true, then we can cross multiply and then see the cross product to see what's up with that. So if this is true, I will just do x times x plus 1, and 1 times the square root. And then because everything is positive, I'm just maintaining all the inequality symbol, right? And then I'll distribute this, I get x squared plus x, and then 1 times the square root of the inside is just the same thing. And then we have x squared plus x is greater than or equal to square root of x squared to the fourth power, square root of x to the fourth power minus x. I don't know if this is true or not, and that's just square both sides. So I can get rid of the square root. If you expand this out, you get x to the fourth power plus 2 times x to the third power plus x squared, and then the square root cancels. We just have x to the fourth minus x. I still don't know if this is true or not. Do more algebra. Let's subtract x to the fourth power on both sides. And then here we have a minus x. Perhaps let me just add the x on both sides. So if this statement is true if and only if the following statement, which is 2x to the third power plus x squared plus x, is that greater than or equal to 0? Do we know if this is true? And yes, we know. It has to be true because we know x is greater than or equal to 2. And we're just adding all these numbers together, and each x has to be bigger than 2, right? Bigger than or equal to 2. So this right here must be a true statement. In other words, we go back, this has to be a true statement as well. So you really have to work out algebra, enough algebra steps to arrive at a statement that you can say that's true for sure. And after you do that, we can say that this integral is bigger than this integral, which is a divergent. If you are bigger than a divergent, you must be a divergent as well. So I'll write down this. This integral must diverge by comparison test, the comparison theorem, with that integral that we just used. So it's an integral from 2 to infinity 1 over x dx. So remember to write down your conclusion and also the supporting statement. So you have to quote which test are you using, and then which item did you use, which is that, and also show me the algebra as well. Notice that I actually didn't work out this integral at all. I didn't touch it at all, right? But then as long as we have two pieces and one of them being divergent, we must know that the whole thing is a divergent because this is like infinity. In another word, that has to be a divergent as well. So we can say that the original integral, which we go from 1 to infinity of the original one, this right here must diverges. And then we are done. That's all.